Bernard. Okay, hello. Here is our lab presentation. If you guys give me a second while I dial this bad boy in. So, hello guys, my name is Sebastian. I have my friend Bernardo on the line as well.
Good evening, Professor.
And basically, we are covering our extra credit lab. So we decided to use Python and applications for mathematics and simulation. As you can see, the first page, I'm going to go on to the next one. The question is, can we make a simulation of dropping a cotton ball? Can the simulation be used to calculate drag? Why do we care? For several reasons. We can create a versatile tool for research, education, teach about structures used in programming languages, compare real-world results to simulated results, and interpret results for better understanding. So what did we do? So what we ended up doing, so we wrote a simulation in Python and GlowScript. And then we implemented the Euler-Kromer method. And then we basically compared the outputs to values from the real world. There is a sample of what our code is, as you guys can tell here. Coming across a little bit of technicalities here, guys.
Technical difficulties will be momentary.
The Euler-Kromer method. For integration here, we have compute forces on particle. And then for momentum, we have it equals mass times velocity. The definition is the force of drag equals the change in momentum over the change in time. We have a final momentum equals initial momentum plus the force times change in time. One thing to note is that we have the final velocity equals the momentum divided by the mass. And then once we updated our position, we know that the equation there is the change in position over the change in time for velocity. In position, we have the final position equals the initial position plus the final velocity times the change in time. And this is kind of the systematic way that we use if we wanted to change anything for our program. Basically, we can just increment the time and repeat, etc., etc. Some of the important formulas used in the simulation are going to be the following. So as you can see here, we have that the magnitude of drag equals the drag constant times velocity squared. A unit vector equals the vector divided by the magnitude. Momentum, mass times velocity. The force of drag, the drag constant times velocity squared times the opposite of the unit vector. The force of gravity, which is mass, the negative of mass times gravity times the j hat. The net forces on an object, gravity plus the drag, the force of the drag. Kind of picking back on the previous slide here, are a little more detailed view of what the codes had. The equations of what we actually use in the code, and you can see a snippet here on the side of what the code is on the right hand side. And then from this point on, we'll have Bernard take over.
I'll be taking over here. So here we have the slide where my friend left off on. So we have here the following. We have the air drag simulation. So this is basically explaining that when the simulation began, the ball is going to be dropped, and the blue ball will only be experiencing gravitational potential energy, MGH. while the red ball will also be affected by the force due to air resistance. Once started, we're going to make a graph of position, velocity, and acceleration with respect to time. And so once the simulation began, the balls were going to be dropped, and the relevant graphs would be outputted to the user. So now this is a part of the presentation we're going to cover Euler-Kromer. So why cover Euler-Kromer method of integration? What is this? Well, if we remember back to our Calc 1 days where we were trying to calculate the area underneath the graph using the most elemental of integration, we remembered how basically what we were doing is getting rectangles or cutting up the graph or the curve into little rectangles, and when we summed up the area of those rectangles, that would give us the area underneath the curve integration. Well, we also remember that the smaller the rectangle, the better resolution or accuracy we would get in producing the proper area underneath the graph. Big rectangles, you'd have gaps. The smaller the rectangle, the more accurate it is. Well, same thing with Euler-Kromer. In this case, what's changing is the time interval. The smaller the time interval, the more accuracy we'll get. In this case, this is the graph of the balls when we use time at 0.2. You might think, well, 0.2 seconds, golly, that's really small. But in reality, for the computer, not so much. We can see how the red graph, which is the one that we care about the most with air resistance, looks a bit choppy. We're expecting something, with some curve to it. And that's not what we see here. So if we move on to the next slide, we're going to use 0.1 seconds. Here we see, something closer to what we're expecting, right? It's still a bit choppy where we're starting to see that it looks like there's a curve happening here, right? Well, look what happens when we go to 0.01 seconds. Here's what we're looking for, right? We have a smooth curve. This is going to be the most accurate of representations. And, we can go 0.00001. We can go as accurate as we want, but for, human consumption, what we want to see on the graph, this is more than enough. This is accurate enough for us to do some math on this and, use this in the presentation and accurately portray what was going on as far as the acceleration of the ball with air resistance versus the one with just MGH. And, we see it here. As soon as the ball was let go of, its acceleration was just constant until it, hit the ground. And that's where it just drops off instantaneously and goes to zero. But if we look at the red ball, we see it starts at, at 10 meters per second, but it slowly, drops off until we reach zero. So structures that we use in the simulation. Well, we use many standardized structures such as the if-else statements. In this case, we had if height 1 was greater than 0, it would execute the following code. Else, if that meant the height had already reached 0, the following code again would also be executed. We also use loops. In this case, we have while h-2 is greater than 0, or while the second height is greater than 0, rate would be set to 10. In this case, we're initializing the parameter rate to the variable 10, and that would execute the relevant section of code. We also use the setting of variables. In this case, this is for a prototype code. We used L, or our length, to 30, our height to 30 in meters, G is 9.8, the mass of the object as 10 kilograms, and the drag coefficient as 0.2. Obviously, this isn't what a cotton ball would be, but just to get some practice. We also obviously had to include input and output to the user, in this case, an explanation, and then EV equals scene.wait for click, which is basically telling the computer, hey, the moment the user clicks, you want to execute the program. So setting up the simulation. Originally, as I said before, we set up a simple program, which was our prototype. But after we consulted and we did some more research, we realized we're going to have to rework this a little bit to make it more realistic, and obviously including the real parameters of a cotton ball. So real world results. This is what we achieved. The mass of the cotton ball, after using some research and our best guess, came out to 0.00062 kilograms. Our height was about 2 meters. Our drag coefficient was 0.00012 kilograms per second, and our time was 1 second. And this is what we plugged into the code as follows. And this is our graph of our position relative to time of the two balls. And if we do some just number checking here, we have our position, and then we take the first derivative to get our velocity. And so let's say time equals 0.4. Let's punch that in. So we punch in velocity at 0.4 is we're going to punch that into the derivative. 0 plus, negative g times 0.04 seconds, and we get negative 3.92 meters per second. And that is, again, what we expect to see in the theoretical. And that is also what we see here in the code. What are we getting? We're getting about, where's our velocity? Yep, we get the slope of that tangent line, which is negative 3.92 meters per second, which is what we expected. Then this is the second graph. This is our velocity with respect to time. Let's do some fact checking here, okay? We're going to take the area underneath the curve, or in this case, the triangle. We're going to use 1/2 base times height. When we compute that, we get our change in position is 1.94 meters. If you remember, Professor, what we punched into the code, and previously we punched in 2 meters as our height for the simulation. We got 1.94, which isn't 2, but close enough to show that our program was accurate. And again, when we go to our acceleration versus time graph, we're also going to do some checking here. We're going to calculate our velocity, which is, again, the area underneath, in this case, of the ball with no air resistance. So we're going to do base times the height, and we get our velocity equal to 6, or roughly 6 meters per second, which, again, when we punch this into the theoretical equations, is what we get. So close enough. So for the conclusion, can we make a simulation of dropping a cotton ball? And can the simulation be used to calculate drag? The answer to that is yes. Yes, indeed, we can. Obviously, we haven't really had any experience with air resistance in this class, and I assume we won't have for a couple of semesters to come. But we were able to get enough research and come up with something rough program, rough simulation. But it allowed us to sort of answer this, rise to the challenge and create the simulation. So yes, we can crudely represent air resistance in our simulation. And that concludes our simulation. Thank you, Professor, for this opportunity for extra credit.
Yes, thanks, guys. Thanks, Mrs. Cal and Dr. E.